Hello my friends and my teacher. My name is MertBaykara and I'm studying in Ege University Mechanical Engineering Department. Today I'm going to talk about nanotechnology in energy applications. This is my overview. What is nanotechnology? What can nanotechnology do? Examples from energy applications. Nanomaterials in energy. Nanostructures in energy applications. Environmental effects. Advantages and disadvantages of nanotechnology. First of all, what is nanotechnology? Nanotechnology is a field of research and innovation concerned with building things, generally materials and devices on the scale of atoms and molecules. A nanometer is a 1/1,000,000th of a meter, 10 times the diameter of a hydrogen atom. The diameter of a human hair is on average 80,000 nanometers. At such scales, the ordinary rules of physics and chemistry no longer apply. For instance, materials' characteristics such as their color, strength, conductivity, and reactivity can differ substantially between the nanoscale and the macro. Carbon nanotubes are 100 times stronger than steel, but 6 times lighter. What can nanotechnology do? Nanotechnology is hailed as having the potential to increase the efficiency of energy consumption, help clean the environment, and solve major health problems. It is said to be able to massively increase manufacturing production at significantly reduced costs. Products of nanotechnology will be smaller, cheaper, lighter yet more functional, and require less energy and fewer raw materials to manufacture, claim nanotech advocates. Some examples about nanotechnology and energy. Generating steam from sunlight. Researchers have demonstrated that sunlight, concentrated on nanoparticles, can produce steam with high energy efficiency. The solar steam device is intended to be used in areas of developing countries without electricity for applications such as purifying water or disinfecting dental instruments. Another research group is developing nanoparticles intended to use sunlight to generate steam for use in running power plants. Producing high-efficiency light bulbs. A nano-engineered polymer matrix is used in one style of high-efficiency light bulbs. The new bulbs have the advantage of being shatterproof and twice the efficiency of compact fluorescence light bulbs. Other researchers developing high-efficiency LEDs using arrays of nanosized structures called plasmonic cavities. Another idea under development is to update incandescent light bulbs by surrounding the conventional filament with crystalline material that converts some of the waste infrared radiation into visible light, increasing the electricity generated by windmills. An epoxy containing carbon nanotubes is being used to make windmill blades. Stronger and lower weight blades are made possible by use of nanotube fleet epoxy. The resulting longer blades increase the amount of electricity generated by each windmill. Generating electricity from waste heat. Researchers have used sheets of nanotubes to build thermocells that generate electricity when the sides of the cells are at different temperatures. These nanotube sheets could be wrapped around hot pipes such as the exhaust pipe of your car to generate electricity from heat that is usually wasted. Storing hydrogen for fuel cell powered cars. Researchers have prepared graphene layers to increase the binding energy of hydrogen to a graphene surface in a fuel tank, resulting in a higher amount of hydrogen storage and therefore a lighter weight fuel tank. Other researchers have demonstrated that sodium borohydride nanoparticles can effectively store hydrogen. Clothing that generates electricity. Researchers have developed piezoelectric nanofibers that are flexible enough to be woven into clothing. The fibers can turn normal motion into electricity to power your cell phone and other mobile electronic devices, reducing power loss in electric transmission wires. Researchers at Rice University are developing wires containing carbon nanotubes that will have significantly lower resistance than the wires currently used in electric transmission grid. Richard Smalley envisioned the use of nanotechnology to radically change the electric distribution grid. Smollis concept these upgraded transmission wires, which could transmit electricity thousands of miles with insignificantly power losses, with local electricity storage capacity in form of batteries in each building that could store power for 24 hours use. Nanomaterials in energy. Graphene-based materials. There is enormous interest in the use of graphene-based materials for energy storage. The research on the use of graphene for energy storage began very recently, but the growth rate of relative research is explosive. Graphene recently emerged as a promising material for energy storage because of several properties, such as low weight, chemical inertness, and low price. Graphene is an allotrope of carbon that exists as a two-dimensional sheet of carbon atoms organized in a hexagonal lattice. A family of graphene-related materials, called graphenes by the research community, consists of a structural chemical derivatives of graphene. The most important chemical derivative, graphene, is a graphene oxide, which is usually prepared from graphite by oxidation to graphite oxide and consequent exfoliation. The properties of graphene depend greatly on the method of fabrication. For example, reduction of graphene oxide to graphene results in a graphene structure that is also one atom thick but contains a high concentration of defects, such as nanoholes and Stonewall defects. Moreover, carbon materials which have relatively high electrical conductivity and variable structures are extensively used in the modification of sulfur. Sulfur-carbon composites with diverse structures have been synthesized and exhibited remarkably improved electromechanical performance than pure sulfur, which is critical for battery design. Graphene has great potential in the modification of a sulfur cathode for high performance lithium-sulfur batteries, which has been broadly investigated in recent years. Silicon-based nanosemiconductors. Silicon-based nanosemiconductors have been extensively studied at Kyoto University. They utilize silicon nanoparticles in order to absorb a greater range of wavelengths from the electromagnetic spectrum. This can be done by putting many identical and equally spaced silicon rods on the surface. Also, the high-end length of spacing have to be optimized for reaching the best results. This arrangement of silicon particles allows solar energy to be reabsorbed by many different particles, exciting electrons and resulting in much of the energy being converted to heat. Researchers from Kyoto University have shown that these nanoscale semiconductors can increase efficiency by at least 40% compared to the regular solar cells. Nanocellulose-based materials. Cellulose is the most abundant natural polymer on Earth. Currently, nanocellulose-based mesophore structures, flexible thin films, fibers, and networks are developed and used in photovoltaic devices, energy storage systems, mechanical energy harvesters, and catalytic components. Inclusion of nanocellulose in those energy-related devices largely raises the portion of eco-friendly materials and is very promising in addressing the relevant environmental concerns. Furthermore, cellulose manifests itself in the low-cost and large-scale promises. Nanostructures in energy. One-dimensional nanomaterials. One-dimensional nanostructures have shown promise to increase energy density, safety, and cycling life of energy storage systems, an area in need of improvement for lithium batteries. These nanostructures are mainly used in battery electrodes because of their shorter, continuous ion and electron transport pathways, which results in higher battery performance. Additionally, 1D nanostructures are capable of increasing charge storage by double layering and can also be used on supercapacitors because of their fast pseudo-capacitive surface redox process. In the future, novel design and controllable synthesis of these materials will be developed much more in depth. 1D nanomaterials are also environmentally friendly and cost-effective. Two-dimensional nanomaterials. The most important feature of two-dimensional nanomaterials is that their properties can be precisely controlled. This means that 2D nanomaterials can be easily modified and engineered of nanostructures. Their special structural feature is interlayer space, which provides the unique engineering option of tuning their energy storage and catalytic properties. The interlayer space can also be manipulated for nanolayered materials, called 2D nanofluidic channels. 2D nanomaterials can also be engineered into porous structures in order to be used for energy storage and catalytic applications by applying facile charge and mass transport. 2D nanomaterials also have few challenges. There are some side effects of modifying the properties of the materials, such as activity and structural stability, which can be compromised when they are engineered. For example, creating some defects can increase the number of active sites for higher catalytic performance, but side reactions may also happen which could possibly damage the catalytic structure. Another example is that interlayer expansion can lower the ion diffusion barrier in the host, but it can also potentially lower its structural stability. Because of this, there is a trade-off between performance and stability. A second issue is consistency in design methods. For example, heterostructures are the main structures of the catalysts in interlayer space and energy storage devices, but these structures may lack interpretation on the catalytic reaction or charge storage mechanisms. A deeper understanding of 2D nanomaterial design is required because fundamental knowledge will lead to consistent and efficient methods of designing these structures. A third challenge is the practical application of these technologies. There is a huge difference between lab scale and industry scale applications of 2D nanomaterials due to their intrinsic instability during storage and processing. For example, porous 2D nanomaterial structures have low packing densities, which makes them difficult to pack into dense films. New processes are still being developed for the application of these materials on an industrial scale. Applications: lithium-sulfur based high-performance batteries. The lithium battery is currently one of the most popular electrochemical energy storage systems and has been widely used in areas from portable electronics to electric vehicles. However, the gravimetric energy density of lithium batteries is limited and less than that of fossil fuels. The lithium-sulfur battery, which has a much higher energy density than the lithium battery, has been attracting worldwide attention in recent years. A group of researchers from the National Natural Science Foundation of China and the Ningbo Science and Technology Innovation Team have developed a nanostructure-based lithium-sulfur battery consisting of graphene-sulfur-carbon nanocomposite multilayer structures. Nanomodification of sulfur can increase the electrical conductivity of the battery and improve electron transportation in the sulfur cathode. Ultra-written sulfur is layered onto graphene nanosheets and covered by a thin layer of amorphous carbon derived from beta cyclodextrin in order to create high-performance lithium-sulfur batteries. These batteries can deliver a high initial discharge and charge capacity of 1410 mA and 1370 mA respectively, and the capacity retention of 63.8% can be achieved after 100 cycles at 0.1 C. A specific capacity of 40-50 mA can be retained after 200 cycles at rate of 2 C. A graphene sulfur carbon nanocomposite with a multilayer structure in which nanosite sulfur is layered on both sides of chemical reduced graphene sheets and covered with amorphous carbon layers can be designed and successfully prepared. This structure achieves high conductivity, size miniaturization of sulfur and surface protection of sulfur simultaneously, and thus gives rise to excellent charge-discharge performance. The GSC composite shows promising characteristics as a high-performance cathode material for lithium-sulfur batteries. How can nanotechnology improve batteries? Using nanotechnology in the manufacture of batteries offers the following benefits: increasing the available power from a battery and decreasing the time required to recharge a battery. These benefits are achieved by coating the surface of an electrode with nanoparticles. This increases the surface area of the electrode thereby allowing more current to flow between the electrodes and the chemicals inside the battery. This technique could increase the efficiency of hybrid vehicles by significantly reducing the weight of the batteries needed to provide adequate power. Increasing the shelf life of a battery by using nanomaterials to separate liquids in the battery from the solid electrodes when there is no draw on the battery. This separation prevents the low-level discharge that occurs in a conventional battery, which increases the shelf life of the battery dramatically. Nanomaterials in solar cells. Engineered nanomaterials are key building blocks of the current generation solar cells. Today's best solar cells have layers of several different semiconductors stacked together to absorb light at different energies, but still only manage to use approximately 40% of the sun energy. Commercially available solar cells have much lower efficiencies. Nanostructuring has been used to improve the efficiencies of established photovoltaic technologies, for example, by improving current collection in amorphous silicon devices, plasmonic enchainment in dye-synthesized solar cells, and improved light trapping in crystalline silicon. Furthermore, nanotechnology could help increase the efficiency of light conversion by utilizing the flexible band gaps of nanomaterials, or by controlling the directivity and photon escape probability of photovoltaic devices. Titanium dioxide is one of the most widely investigated metal oxides for use PV cells in the past few decades because of its low cost, environmental benigni, plentiful polymorphs, good stability, and excellent electronic and optical properties. However, their performances are greatly limited by the properties of the titanium dioxide materials themselves. One limitation is the wide band gap, making titanium dioxide only sensitive to ultraviolet light, which just occurs less than 5% of the solar spectrum. Recently, core shell structured nanomaterials have attracted a great deal of attention as they represent an integration of the individual components into a functional system, showing improved physical and chemical properties, which are unavailable from isolated components. For titanium dioxide nanomaterials, this core shell structure design will provide a promising way to overcome their disadvantages, thus resulting in improved performances. Compared to SOL, titanium dioxide material, core shell structured titanium dioxide composites show tunable optical and electrical properties, even new functions, which are originated from the unique core shell structures. How can nanotechnology improve solar cells? Using nanoparticles in the manufacture of solar cells has the following benefits: reduced manufacturing costs as result of using a low temperature process similar to printing instead of the high temperature vacuum deposition process typically used to produce conventional cells made with crystalline semiconductor material. Reduced installation cost achieved by producing flexible rolls instead of rigid crystalline panels. Cells made from semiconductor thin films will also have this characteristic. Currently available nanotechnology solar cells are not as efficient as traditional ones. However, their lower cost offset this. In the long term, nanotechnology versions should both be lower cost and, using quantum dots, should be able to reach higher efficiency levels than conventional ones. This is the photovoltaic device efficiency divided cost. Nanoparticle fuel additives. Nanoparticle fuel additives. Nanomaterials can be used in a variety of ways to reduce energy consumption. Nanoparticle fuel additives can also be of great use in reducing carbon emissions and increasing the efficiency of combustion fuels. Cerium oxide nanoparticles have been shown to be very good at catalyzing the decomposition of unburned hydrocarbons and other small particle emissions due to their high surface area to volume ratio, as well as lowering the pressure within the combustion chamber of engines to increase engine efficiency and curb NOx emissions. Addition of carbon nanoparticles has also successfully increased burning rate and ignition delay in jet fuel. Iron nanoparticle additives to biodiesel and diesel fuels have also shown an increase in fuel consumption and volumetric emission of hydrocarbons by 36%, carbon monoxide by 6-12%, and nitrogen oxides by 4-11% in one study. How can nanotechnology improve fuel cells? Catalysts are used with fuels such as hydrogen or methanol to produce hydrogen ions. Platinum, which is very expensive, is the catalyst typically used in this process. Companies are using nanoparticles of platinum to reduce the amount of platinum needed, or using nanoparticles of other materials to replace platinum entirely and thereby lower costs. Fuel cells contain membranes that allow hydrogen ions to pass through the cell, but do not allow other atoms or ions such as oxygen to pass through. Companies are using nanotechnology to create more efficient membranes. This will allow them to build lighter weight and longer lasting fuel cells. Small fuel cells are being developed that can be used to replace batteries in handheld devices such as PDS or laptop computers. Most companies working on this type of fuel cell are using methanol as a fuel and are calling them DMFCs, which stands for direct methanol fuel cell. DMFCs are designed to last longer than conventional batteries. In addition, rather than plugging your device into an electrical outlet and waiting for the battery to recharge, with a DMFC, you simply insert a new cartridge of methanol into the device and you are ready to go. Environmental and health impacts of fuel additives. While nanomaterials can increase energy efficiency of fuel in several ways, a drawback of their use lies in the effect of nanoparticles on the environment. With cerium oxide nanoparticle additives in fuel, trace amounts of these toxic particles can be emitted within the exhaust. Cerium oxide additives in diesel fuel have been shown to cause lung inflammation and increase the bronchial alveolar lavage fluid in rats. This is concerning, especially in areas with high road traffic, where these particles are likely to accumulate and cause adverse health effects. Naturally occurring nanoparticles created by the incomplete combustion of diesel fuels are also large contributors to toxicity of diesel fumes. More research needs to be conducted to determine whether the addition of artificial nanoparticles to fuels decreases the net amount of toxic particle emissions due to combustion. Environmental effects. Some of the more extravagant negative future scenarios have been debunked by experts in nanotechnology. For example, the so-called Grey Go scenario, where self-replicating nanobots consume everything around them to make copies of themselves, was once widely discussed but is no longer considered to be a credible threat. It's possible, however, that there will be some negative effects on the environment, as potential new toxins and pollutants may be created by nanotechnology. Advantages and disadvantages of nanotechnology. Energy advantages. Nanotechnology may transform the ways in which we obtain and use energy. In particular, it's like that nanotechnology will make solar power more economical by reducing the cost of construction, solar panels, and related equipment. Energy storage devices will become more efficient as a result. Nanotechnology will also open up new methods of generating and storing energy. Disadvantages. Health and safety issues. Nanoparticles can cause serious illness or damage the human body. Carbon nanotubes could cause infection of lungs. Mass production in food and consumables, oil and diamonds could become worthless. Loss of jobs in manufacturing and farming, etc. Atomic weapons could be more accessible and destructive. Increase social strife through increasing wealth gap. Nanopollution is created by toxic waste. And this is my sources. I hope you are satisfied with my presentation, and sorry for my pronunciation mistakes.